Yesterday, this session, there are two talks, but order is changed because it is better, it is more reasonable. So the first speaker is Jeremy. So yeah, please.
Okay, thank you. Okay, so yeah, my talk's gonna be a little different. So I'm not I haven't done any work on free-floating planets. My usual title would just be planet formation in misaligned circumbinary disks, but then I just tagged this on to try and make a connection to free-floating planets. But my work, we had a nice talk from Gavin this morning that introduced that binary systems can be a source for free-floating planets. And so I'm going to talk about how you can form planets in binaries, and I'll mostly talk about the disk stage because we know that's where planets form. And then part two of the talk will be given by Chang. So he'll talk. I'll try and convince you that planets can form in binaries, and then Chang will take over and talk about how these tilted planets can be progenitor of free-floating planets. Okay. So this is a kind of a review from what Gavin said. But binary star systems are common in the galaxy. To the most recent Gaia catalog, about 1 million binaries so far. And so since these binaries are the majority of stellar configurations, it's really important to study how planets and the disk dynamics around these binaries evolve in time. So when we image these these binary systems, we commonly see circumbinary disk around these binaries. So these are two examples, AK Skull and AC900b. But when we look closer in these observations, the disk is commonly misaligned to the binary orbital plane. So it's different than single stars. Usually the disk and star are kind of on a similar plane. But when you form binary stars, it's a very chaotic environment. You have accretion coming in at different angular momenta, which just create a disk at an arbitrary inclination. Okay. So I just want to test you guys first. So based on these images here, we'll start with AK Skull. What do you think the misalignment is? You see the binaries right here, and the disk is here. So anyone have a guess on the misalignment between these two? Just like throw out a number. It's between 0 and 180. 30. One more guess? 179. Okay, this is actually 0. So it's actually coplanar. Okay? What about HG900b?
90.
It is 90. All right. So this is actually a polar aligned disk, right? So you have one that's coplanar and one that's polar. Both these configurations are stable. Okay. So I'll kind of explain more about that in the future. So we know that these disks can be the site of planet formation. So you can kind of form two types of planets in binary systems. You can form these S-type planets, which are just the planets around the individual components. So you have circumprimary or circumsecondary planets. Or you can form these circumbinary planets, which are P-type, called P-type planets. So they orbit both the stars. I think Cheng has a picture of this, but if you see Star Wars, you see Tatooine. In the background, there's 2 stars around Tatooine. So Tatooine is an example of these P-type planets. And so far, we know about 20 or so Tatooine-like planets that exist in the galaxy. And this is a table of some of these systems here. We showed the signature axis of the binary, given by these yellow dots, and then the planets, the corresponding planets for each system. So at most, we've detected 3 circumbinary planets around the binary. You can see that these horizontal lines here on the plot is the tidal truncation radius, or the stability radius. So you notice that all planets have to be beyond that, or else if they're interior to that, they'll be unstable, which is what Gavin mentioned this morning. But you can see that most of the planets will tend to migrate through the disk and kind of stop at this cavity edge, which is just outside the stability region. Okay. But like I mentioned before, when we look at these disks, we commonly see a misalignment. So this is a nice image from Zizkala 2019. The y-axis shows the misalignment angle, and then as a function of binary orbital periods. And so we have these 3 different objects here. We have planets, coplanetary disks, and debris disks. So you notice that when a binary is very close in binary, everything is coplanar. The torque of the binary is really good at aligning everything on the same plane. Okay? But when you have more wider binaries, things can become more misaligned. And what's interesting here is that you see the planets are in blue. All the planets that we detect around binaries are all coplanar to the binary orbital plane. But we see no planets that are misaligned, but we see misaligned disks. So there's a discrepancy there. So why we see misaligned disks, but we don't see misaligned planets? There's 2 reasons. Misaligned planets are really hard to detect. even through transits or something like that. So they could be very hard to detect, or they could be a source of free-floating planets. So what Cheng will talk about next is that these misaligned planets could be more prone to being ejected from these systems. So maybe that's why we don't see them. Okay? So a misaligned disk won't stay misaligned, it will undergo alignment. So for a lowly inclined disk, I have just a simple cartoon here where you have the angular momentum vector of the binary in blue and the disk in red. When it's lowly inclined, the disk will precess about the angular momentum vector of the binary, and due to viscous heating, the viscous dissipation, the disk will eventually align and it will go coplanar. So the disk angular momentum vector will align to the binary. In case for a more highly inclined disk, instead of the disk precessing about the angular momentum vector of the binary, it will precess about the eccentricity vector of the binary, and then it will align to that, and you have a stable polar disk. So both these configurations are polar, and we know, I mentioned one polar disk, we know about there's like two more polar disks that we know around binaries. So you can have these two stable configurations, but we have misaligned disks. Misaligned disk will evolve to one of these two states. And you can actually estimate the alignment time scale, again, by this simple equation here, which depends on the viscosity of the disk, the disk aspect ratio, so how thick the disk is, your binary angular frequency, and your global disk precession frequency. And so this precession frequency changes if you're going polar or coplanar. Okay, I won't go into all these equations, but it just depends on surface density profile of the disk and whatnot. But in general, a disk that's going polar aligned will align faster than coplanar. Okay? So here's an example of some simulations I ran. Each color is a different initial inclination of the disk to the binary. So I have this dark green is starting at 0. Dark blue is it's a retrograde, so it's 180, and I have increments of 15 degrees. So you can see here, like the greener, these three simulations will evolve coplanar to the binary, so eventually they go down to 0. The blue ones will evolve coplanar as well, but they're retrograde, and then you have these ones in the middle here, which will go polar. You can see there's like a critical tilt. It either goes polar or coplanar to the binary. And this critical tilt depends on the angular momentum ratio of the binary to the disk, and also the binary eccentricity. So in this case, I set the binary eccentricity to 0.5, which critical is about 38 degrees. So anything above 38 degrees will align polar. A disk that's below 38 degrees for this binary would go coplanar, or if it's above 142, it would go retrograde. Okay, so it's kind of 3 stable configurations. But you notice that the disk doesn't go straight to. If you start at 30, it just doesn't go straight to 0. It has these oscillations. And so these oscillations are from the torque of the eccentric binary. And so this can play a factor in planet formation, because if the alignment time scale is longer than a disk lifetime, which is about 1 to 10 million years, the disk will never fully align coplanar. And so you always have a misaligned disk, and you can form misaligned planets. Okay, so it really depends on this alignment time scale. But in general, again, you can see from these simulations, the polar one alignment is a lot quicker, but you can kind of tune the disk parameters and the binary parameters where you can elongate this alignment time scale. On the right here, this is just a phase diagram. So I is the tilt of the disk, and the phi is the longitude ascending node. So which gives you, it basically gives you the precession rate of the disk. So d phi over dt is the precession rate. And you can just see it, for example, the green here, which are going to go coplanar, they're going to spiral inward into 0. The red ones are going polar, they're going to spiral into around 90 degrees. So this is showing their kind of evolutionary pathway. Okay. Eve mentioned this in her talk about the coupling of dust grains. So when we want to talk about planet formation, we need to look at how the gas and dust interact with each other. And so we're looking at the misaligned disk. We have the Stokes number, which depends on the surface, the density of the dust, the size of the dust, which is S, and over the surface density of the gas. And so if you have smaller grains, this is not really good. As Yves mentioned, the grains will go to align to the midplane, but this is just for representation regions that I just put it kind of sporadic. But for smaller grains, for your Stokes number less than 1, it'll be well coupled to the gas. And so as the disk precesses, the dust is going to precess at the same rate as the gas, okay? For low Stokes number. But for higher Stokes number, on average, or 1 on the greater, these dust particles are now weakly coupled to the gas. So as this misaligned disk is precessing, the dust and gas are gonna process at different rates because the dust is not well coupled to the gas. Okay, so this differential precession is very important for this talk. So just keep that in mind. Okay, so we want to look at how the dust reacts in a misaligned disk. This has been looked at before by my collaborators, Hassan Ali and Cristiano Longarini, back in 2021. So when you have a misaligned disk, which I mentioned before, if you have moderately coupled dust grains, they'll process at different rates. This differential precession actually creates a dust traffic jam in the disk. And this is where an area around, it's a little complicated, but it's an area around the co-precession radius. So the co-precession radius is the radius at which gas and dust will process the same rate at that point in time. Around that co-precession radius, you get your velocity difference kind of goes to 0, and so there's no radial drift that occurs, and you get this dust traffic jam, so this pileup of dust. And this is different than a traditional dust trap because there's no pressure gradients at that location. It's just due to a traffic jam, so everything's just slowing down at that location, and it creates a coherent dust ring. And so to investigate this, I use smooth particle hydrodynamics, so SPH. I use the code called Phantom, which is widely used in star formation, binary disks, which I'm talking about, or even like embedded planets. So it's a very versatile code, and it's been used for over a decade. So here's my setup. So I'm going to look at how the gas and dust evolve in a polar lining disk. But I will note that this effect will also happen for a disk that's going coplanar. Okay, so if you just have a misaligned disk around the binary, you'll get this effect. Okay, what I'm showing here on the top is the surface density of the gas, and then the bottom row is surface density of the dust. And my simulations are in 3D, so that's why I have 3 different panels: the XY plane, XZ plane, and YZ plane. So in this simulation, my disk is highly misaligned, about 60 degrees relative to the binary plane. And so this disk will go polar aligned. And as it's misaligned, as it goes polar, it develops these dust rings, if you look on the bottom right panel. And these dust rings are a byproduct of these dust traffic jams. And these dust traffic jams are stable throughout the simulation. I can have to speed up. And so what we're showing here is this is the top panel here is the surface density of the gas and dust. The gas is in black, dust is in red. Middle panel here is the inclination, so they both start at 60 degrees, and the bottom one is a phi, which again gives the precession rate. So as the disk is precessing around, they're going to precess at different rates if you look at the bottom panel, and they create this dust traffic jam, the first one here, and you keep generating these rings further and further out in the disk because the gas and dust components in the outer parts of the disk are still misaligned. So it takes a while for this whole disk to become aligned. You can see the inner parts of this are aligned. So the engine to create these dust traffic jams is turned off, but the outer parts are still misaligned. And so this will keep creating dust rings further and further out in the disk until the whole disk is aligned. And so here's just the surface density of one of these dust rings. I don't have time to skip that. You can vary the different dust sizes. Again, you get these dust rings. You can vary different parameters of the disk. So you can look at the disk thickness, surface density, different sound speed profile, different viscosity. This process is very robust, and so you get these dust traffic jams produced. Okay, and if you look at the mid-plane dust to gas ratio in these rings, they're heightened, so they reach above 1. So that means you have more dust than gas in these rings. And nice talk from Yuki just mentioned that you can create these protoplanets in these rings. So these rings are very important. And so one way to create these protoplanets is that you first have to come from really small grains to larger grains, but you have this meter-sized barrier. So one way to overcome that is called the stream instability, which is basically a process where you have the drift between the solid and the gas create these clumps. This is from Nasvarny 2019, and get these clumps can self-gravitate and form these planetesimals. Okay? So that's one way to kind of get over this meter-sized barrier. And so I did a very simple 2D fluid equation and shearing box based on the parameters of my simulation. And so in these dust rings and these circumbinary disks, you can get heightened, if you look at this red region, you get heightened this is the distributed instability growth rate. So enhanced growth rate inside these dust traffic jams, which will promote grain growth and eventually growth of protoplanets. And these rings can be misaligned, and so you can form these misaligned planets. And then again, real quick, in the future, since this effect only happens where you have marginally coupled dust grains, so they're relatively large, you can maybe detect this through NGVLA, which is up and coming telescope, and this is just a synthetic observation of one of my disks. Just to wrap up, just to go back to this point that we see a lot of misaligned disks, but we don't see any misaligned planets. So one reason is that misaligned planets could be hard to detect, or they could be a progenitor of these free-floating planets in the systems, and you'll see what Chen will talk about that next. So I'll leave my summary up and I'll take any questions.
So you didn't talk much about the retrograde option, and maybe that's not very common, but also I had some questions. So first of all, when you're finding circumbinary planets by transits, are you going to be? Can you distinguish between the two, or do you get the wrong parameters? And then the other question is also the retrograde orbits are presumably have like a different stability limit.
Yes.
And so you can maybe get planets in much closer.
Right. So does polar too. I didn't mention that, but for a polar disk, the torque from the binary onto the disk is almost zero. So the cavity is much smaller than the polar disk, also retrograde disks. So you can get closer planets in for polar if you have any polar planets or retrograde planets.
Right. Yeah. But I mean, is it known that the retrogrades are really a lot rarer than?
Yeah, I don't know of any that we know of any retrograde disks around.
Right, but okay. Yeah, so like for transiting planets, can you tell whether any of them are
to my knowledge, I don't think so. I'm not an observer, so yeah. So I'm not sure. I don't know if I think the signal is pretty much the same if it's going prograde or retrograde. If you're looking at the edge on.
Right.
Yeah.
The radii.
If you mean the planet could be closer to the.
Well, I mean if the stars are orbiting in the same direction as the planets, then the transit.
Yeah, I mean, I guess you can calculate the orbital period right from the transits, and so if it's closer in, if it's inferior to this stability limit for a prograde case, then maybe the planet's actually retrograde.
Oh, but the measurement of the radius could be wrong if you get the wrong velocity.
No, you do dynamically. No, you can determine. You know the orbital phase of the binary, so you can determine the relative motion between the binary from the transit duration, and so you completely solve the system. I don't think you can mistake it as a retrograde.
Thank you.
It might be harder to detect the first ones.
Yes.
Yeah.
Okay, hold on. So I'm wondering if the back reaction, circular back reaction from the disk to binary is important.
Yeah,
like
good question.
Those cause a like circular interaction.
Yeah. Just like so, in our simulations, we
Fix the binary?
No. The binary can evolve, but the disk is low mass. So we do it low mass so that that doesn't have much effect on the binary. But if you have a massive disk, it will affect the orbit of the binary, and that will mess up the dynamic. So that's one thing I maybe want to investigate is kind of this process in a massive disk. Yeah, well, I haven't done that yet.
Nice. Thank you.
Yeah, good question.
Right. So,
Yeah.
This is a cool talk. I really like this stuff.
Yeah.
Question. So the stuff you're showing the rings, that was for large Stokes numbers, right?
Yeah, I mean the smallest grain size was about 0.7 centimeter in those simulations.
Is there any barriers? Like, are the barriers to dust growth any different in
Well, I
this
think-
kind of disk compared to normal?
From my knowledge, we can get to centimeter sized grains, but I think it's the meter sized barrier, right? So it's getting from probably planetesimals from these pebbles. But yeah, so that's one thing I wanted to look at is so Phantom can actually do this grain growth and fragmentation. It's very simple, but I think it's a good place to start. But I want to look at kind of modeling that and see if we get any collisions and stuff in these rings. But I don't think anyone's really looked at growth of dust around binaries yet.
so yeah.
So just to follow up on that, I thought that the relative velocity between dust particles is much higher in those systems where you have a binary, so I fragment the dust particles rather than. You also excite eccentricity.
Right. I mean, I guess it depends on where you are in the disk. So if you have a very large disk, the grains further out will just feel like the binary is just a single star potential. So I guess it depends on the radii of the disk, the radii of the dust.
Okay, so just time. So thank you very much.